Welcome to today's video. Today we're going to introduce three notions that are going to be very helpful. The notion of proper time, co-moving frame, and line element, of which you've seen already a tiny little bit. And after that, I'll do a couple of examples of relativistic trajectories so you understand how to get the relationship between the time in one frame as compared to the time in a different frame, and in particular, frames associated with trajectories in spacetime. That's going to be the video today, in preparation for the next video where we will see Lorentzian tensors and the Poincare group core when we look in the eye at what special relativity is. All right, let's do it. Let's begin with the notion of line element. What do I mean when I say line element? Well, the spacetime interval we defined in previous lectures is between two events, say E1 coordinates T1 x1, and another event E2 coordinates T2 x2. The spacetime interval between them, defined as delta S squared, it was c squared delta t squared, which is the difference between these two times squared, and x2 minus x1 squared. Okay, so the difference between these two distances modulo squared. Now, the spacetime interval you can think now, I mean, as a first approximation to the concept of line element, you can think of imagine two events that are differentially close to each other. So you get tx, another event t plus delta t, x plus delta x. So that yields something that is really small if you want, that is the line element d squared between two events that are really close, right? Of course, this definition is very physical in the sense of like physics. Understanding more rigorously what this object is will happen, and it will happen later on in the course after we see differential geometry, and we can understand this as somehow the action of the metric on two elements of the basis. But for now, we're not going to say anything like that. For now, let's think of this as a limit when you consider two events that are really very, very close, as an infinitesimally close, as you often do in physics. Now that we introduce what the line element is, let's introduce the notion of proper time. What is proper time? Let's see. The notion of proper time that I wrote here is that proper time, we call it tau, this is my tau, of a moving particle, is the time measured by a clock that moves with the particle. As simple as that. So my proper time is when I look at my watch and I count time there, that's my proper time. And that's the same for everybody that goes around. You move around, your clock tells you your proper time. The time, in other words, another way of saying it is the time measured in the particle's proper reference frame. I have a reference frame, I'm at the origin of that reference frame, and I have a measure of time, and I have rulers, or I have this. So my watch, my measuring tape, give me my proper frame, okay? All right, I measure with this reference, with this tape, and then I measure time with this clock. That's my proper frame. All right, so keep in mind that in general, this is not talking about inertial frames, and that's really important because what you have probably seen in previous relativity courses is changes of frame where things move with relative velocity with respect to each other. So inertial reference frames. And then you talk about, oh yeah, the gamma tau, you talk about time contraction, time dilation, space contraction, and things like that when you are in an inertial reference frame. Well, that's not really all that it is. I mean, in general, whatever moves can have a non-inertial trajectory. So imagine if I have a trajectory that let's call it the lab frame. In some inertial frame, the trajectory is x of t. Well, the trajectory could be anything. I mean, if I draw, we will be doing this more, but if I draw a space-time diagram and I move like this, sure, I'm moving inertially with some speed. If I'm moving inertially here, co-moving with the lab. So if I stay at x equals 0, it means that I don't move with respect to the lab frame, but I move towards the future. We're always moving in space-time. Then here I'm moving with some speed. That is all inertial. But it could be the case that perhaps I am moving like that, right? Non-inertially. And I still have a proper time. And we can still study this from the point of view of special relativity. So, indeed, proper time is not an inertial frame time in general. Okay, and we will see that. And we will see actually two examples now afterwards of trajectories. There are non-inertial trajectories, and we can still compute the difference in time between some lab frame that is inertial and those other frames, right? Anyway, so it's clear. Proper time is the notion of time as measured by the thing that's moving with respect to me, or with respect to anybody else, okay? The thing that's moving with respect to some reference frame. and the thing that moves as a clock, proper time. All right, let's talk now about the notion of comoving frame. The comoving frame, I denote it here with t prime x prime, for example, the coordinates of the comoving frame. The comoving frame is the name we give to the family of inertial reference frames in which the particle is instantaneously at rest. So think of this as the following. At every point in the trajectory of the particle, there is an inertial frame that is instantaneously not moving with respect to the particle. Of course, the particle will in general be non-inertial, and therefore, according to that frame, is going to start moving one instant after, right? But then the comoving frame is a different one at that instant. At a different instance, right? You get a different comoving frame in which the particle is instantaneously at rest. And all of them are inertial. So you can think of it as all the inertial frames. For example, if I accelerate like that, I started with low speed and I increase the speed. So my proper frame is always my clock and my measuring tape, right? Or my spatial reference frame. But what would have been the comoving frame? The comoving frame is many inertial frames, each of them with the velocity I have at every point, that I'm not moving with respect to every one of them at every instant in my trajectory. So not to confuse the comoving frame and the proper frame. The proper frame is in general non-inertial. The comoving frame always are inertial frames, okay? Now I wrote here 3 frames. The last frame, this is some inertial reference frame that we consider our reference, for example. Then the comoving frame of a particle, let's say you have a particle that moves. Particle, you can write particle trajectory. The particle trajectory, let's write it at x of t, is parameterized in terms of the last frame. Some trajectory that I see in the lab of something moving, just say a fly that is flying. And that fly has a proper frame, tau psi, and with that fly I can associate many comoving frames at every instant, frames that are inertial, and for which the fly is at rest at every instant in its trajectory. The comoving frame is extremely helpful because I know how to do changes. Remember, we found the Lorentz transformations, the Lorentz boosts, that allow us, together with rotations and translations, allow us to relate 2 inertial frames. The time in one inertial frame and the time in another inertial frame, right? But we haven't learned yet how to relate the time of some inertial frame with the time of some non-inertial frame, or 2 non-inertial frames to each other. Does that mean that I cannot do that in special relativity? Well, you can. And this is the thing for which the comoving frame is really useful. Because instantaneously, the comoving frame is inertial and it's also instantaneously coincided at every instant, coincides with the proper frame. Again, it's a different comoving frame every instant, but differentially, right, if you go in really small amounts of motion, then you're going to have an inertial. Every trajectory, even if non-inertial, is differentially inertial. It's the same thing as every smooth curve, it's going to be a straight line if you move little enough. See what I mean? Okay, so I wrote here the space-time interval as we know it, right? And then this is the space-time interval between 2 events in a given frame, say the last frame, for example. So I have 2 times t2, t1. I compute the difference between them. I have 2 positions, x2, x1. That could be, for example, a particle moving, right? And then the event where the particle starts moving. At time 1, x1, the particle is here, then moves. At time 2, the particle is at x2. So you can compute the space-time interval between these 2 points. But I can also, if I'm the particle that's moving, I can also compute it in my own reference frame, right? So if I'm moving with a trajectory x of t, this is my trajectory, right? And then that trajectory x of t is the trajectory I'm describing, for example, could be like this. My position is a function of t, right? So I can describe in my own proper coordinates, I can describe 2 points on my trajectory. I can look at my watch and then measure with my measuring tape. And then I can, after some time, and I look at other events, whatever other events, and I look at my watch and I measure where the other event is, and that will give me the space-time interval as computed by myself, my own proper frame. In particular, I can compute the space-time interval between 2 events on my trajectory, on my own trajectory. For example, I can compute, I'm moving like this, and I look at the clock, at my watch, and I annotate the time, and I measure where I am. It's easy though, because if I measure where I am exactly at the origin, because my proper frame I carry with me, right? And then after some time, I look at my clock, I measure my time, and also measure my position, which is also going to be 0, because I carry my own proper frame with me. So, very interestingly, I don't know where my marker is. Let's summon it. Marker! All right. The magic of crappy video editing, I can never lose anything. Anyway, so we have the proper frame. In my proper frame, we know like for any 2 points in the trajectory of a particle, for any 2 events in the trajectory of a particle, delta psi will be 0. Because of course, a particle is always moving, it's always taking its proper frame with it. So the increase in position that I had when I'm moving is 0 as measured by me, because I'm always here at rest with me. Okay? Right. So we see here that in that case, for any 2 events in the trajectory of a particle, then you know that delta squared is equal to minus c delta tau squared. And that is extremely interesting, because that tells you that an interval of proper time it's equal to the spacetime interval. Huh? How is that? Interesting. Let me define now proper time interval, this delta tau square, as the time interval between 2 events in the frame in which they happen at the same position. Now, you can wonder, is there only one frame in which that happens? And is there always a frame in which that happens? Well, we haven't seen that yet. We will see it in the next lecture. But at the very least, you know that if I'm traveling in a trajectory, certainly 2 events in my trajectory are the amount of time that I measure with my watch in 2 events in my own trajectory. That is a proper time. That is a proper time interval, because these 2 events happen at position 0 in my own frame. Okay? Now, notice also that c squared is a Lorentz invariant. This thing doesn't change with the change of inertial reference frame. So the amount of proper time between 2 intervals, that can be satisfying something like that, 2 events that there is a frame in which they happen at the same position, that amount of proper time is a Lorentz invariant. So that is really, really important. Proper time is kind of the same as the proper time kind of behaves very similarly to the space-time interval. So basically that means that the amount of time in my trajectory that I take to go to 2 points in my trajectory, the amount that I measure, will be the same for everybody. This is not the same as saying the amount of time that I measure that it takes you to get there is the same that my neighbor measures. No, different people will measure different times. But different people would agree that the time that I measure, the time that my watch tells me, is the same. It's not going to change. My time, if it's 13 seconds for me, that person over there will say, oh, it was 13 seconds for him. It was maybe 26 for me, but it was 13 for him. And the other person will say, yeah, it was 32 for me, but it was 13 for him. So the amount of proper time, it's literally a space-time interval. You can tell, well, there's a c square, right? But that doesn't matter. And it's a sign, but that doesn't matter. The amount is the same. So the amount of proper time and the amount of space-time interval are proportional to each other. And therefore, if this one is Lorentz invariant, doesn't change with the change of frame, this one also doesn't change with the change of frame. Because c is a constant, which is the speed of light as measured by any inertial frame. And no matter what frame you are, the speed of light, depending on how you define it, may be different or not, but c, the constant, which is the speed of light in an inertial frame, is a constant that will not change. All right? So certainly, this is like having a 2. So certainly, this delta tau is Lorentz invariant. So whenever you have 2 events that you can join with a physical trajectory or something moving, there is a proper time interval, and that will give you the space-time interval. How clean is that? We will see more about under what conditions you can find proper time. You can find a frame where 2 events happen at the same position. All right, I'm going to define one more thing before moving to the next thing, and let's see what that is. The notion of proper length is very complementary to the notion of proper time interval, which is proper length is the spatial distance between 2 events in the frame where those events happen at the same time. Now, I'm not going to tell much more about that, just take it as a definition, because in the next lecture, when we talk about what the Lorentz group does with spacetime, we're going to talk about time-like, space-like, and node separation, and under what conditions you can find a proper time interval, and in what conditions you can find a proper length between 2 events. Okay? Now, for now, let's leave it as the level of defining the concepts, and let's notice something. Now, of course, if I want to relate, our objective is going to be now to relate my time, let's say my proper time, with the time of the lab, of someone in the lab, some inertial frame. and we're facing the challenge that we don't know how to the Lorentz transformations in principle don't tell you how to transform from an inertial frame to a non-inertial one. So we need to be clever about it, and let's be clever about it. Okay, so I gathered here many things. So let's see. Imagine that I have a particle that is moving with some trajectory that in the lab frame, say that I have somebody sitting at the corner of the room, and they're describing the trajectory at some position that depends on time, right? That is the trajectory of for example, I don't know, if I'm not moving with respect to the lab frame, that would be, for example, x0, always at some position, right? If I'm moving with some speed, well, whatever it is, so imagine it would be some x0 plus vt, right? That would be the trajectories. But I could be moving non-inertially, okay? So I wrote an arbitrary trajectory. It could be anything. I could be just flying around like a fly or whatever, okay? Now, this is the trajectory in the lab frame in some inertial reference frame, but I also wrote here the particle's comoving frame. Different, remember, I use t psi for the proper frame, I use t prime x prime for the comoving frame, and I use tx for the lab frame. Now the comoving frame is inertial. The proper frame is non-inertial. The comoving frame is inertial. But it so happens that at every point it coincides exactly with the proper frame and the comoving frame are the same instantaneously. So this is interesting because it means that something that is moving inertially, if something is moving inertially, the comoving frame is the same as the proper frame. But if you're moving non-inertially, comoving frames are the instantaneous inertial frames that always follow in my movement. So let's see. The comoving frame, and remember that is kind of the family of frames in which I am exactly at rest with at every point in my trajectory. This thing moves itself, right? The comoving frame is co-moving with the particle, but it's inertial. So the trajectory is, right, x, let's say that they, without loss of generality, let's assume that they share an origin, the comoving frame and the lab frame, because of course the comoving frame only needs to be in the same state of motion so that I'm at rest with it. It doesn't have to be really sticking to me. I could move it to a different point in space. So let's make the zero, the origin of the comoving frame, be the same as the origin of the lab frame, which I can do. But at every instant, that frame has a velocity that matches mine. That's the comoving frame. So in that case, the trajectory of the comoving frame would be like this. V of t times t, where the velocity depends on t, and it depends on t like this. Like it's the derivative with respect to the lab frame of the trajectory. So that is a comoving frame. That's the trajectory of the comoving frame. Wonderful. Keep in mind that at every point in time, the comoving frame is moving at the speed v that coincides exactly with the speed of the particle that's moving. Okay? But at every time there's a family of frames. At every time you can consider the corresponding comoving time at every time is the one that has the speed that matches the speed of the particle at that particular, the velocity of the particle at that particular point. All right, so I don't know how to relate the lab frame with the proper frame because the proper frame is non-inertial in general. But I know how to relate the lab frame with every single one of the comoving frames. And then you would say, well, but that makes no sense because you pick one of them and that's only comoving for one instant. One instant after is not that one, so why is that helpful? Well, because at the differential level, they coincide exactly. We know that differentially, we know that d tau would be the same as d tau prime. Because at a given time, so if you take an amount of time that is really, really, really small, talking physicists here, we are the comoving frame still co-moving with me because I haven't had enough time to leave it behind. So yeah, at every instant, instantaneously, at every point, the comoving frame coincides with the proper frame. They don't. If it's not true, this is not true. This is, or deltas, if I integrate this, the deltas here. This is certainly not true at all. That doesn't make sense actually. But differentially it is true because at every instant I have an inertial frame different at every instant. But that's exactly what you do when you integrate something. You add a lot of small little things to give the transformation that is valid for the whole interval. So I'm going to be summing tiny bits of, I got a little bit of a time interval. I transformed that one using, a little bit of a proper time interval. I transformed that one because I know the comoving frame, the little bit of time in the comoving frame will be the same because they're really, really, really tiny. And the comoving frame is inertial, so I know how to transform it using the Lorentz transformation. I know how to transform it to lab frame. So I'm gonna use at every instant the comoving frame, and that changes at different times, but I'm gonna integrate, summing up all the little bits that are transformed because, at every time I'm inertial with respect to a different frame for a little tiny while of time. A differential is small time while of time. I'm going to add all of those differentials and I will get the full amount of proper time. And that will allow me to relate proper time with lab time. Okay? I hope that's clear. Again, ask questions in the live sessions and rewind and think about it again. This is true at the differential level. It is not true when you integrate, of course, because you get a different comoving frame at every point in the trajectory. Let's see how you do it. The first thing that I do is say, okay, I don't know how to transform, how to relate d tau and dt, but I know how to relate d tau prime and dt because they're both inertial. The relation is a Lorentz transformation. So first, let's use the fact that d tau is differentially equal to dt prime, proper comoving, okay? And then I use the differential of this transformation, which gives me this. How did I do that? Well, I took this transformation and I know, well, I'm moving in a trajectory. This is a function of t now. And I take the differential here and here, so differential t prime, and then is gamma, derivative of this with respect to t, differential t, so just gamma dt, minus, and then I differentiate this thing, and I'm gonna get the velocity when I differentiate that, right? The derivative of xi of t is dx dt, which is the velocity as a function of time, and differentiating one, I get exactly this. All right, but then I realized, what is this? Why did I write gamma of t? Well, because gamma is, of course, gamma of t is the Lorentz factor that we saw before, is square root of 1 minus v of t squared divided by c squared, right? Now the velocity depends in time, that's the trajectory. So you see this guy is inertial, but with a velocity that is different at every time. So at an instant, because we're operating differentially, this is inertial. I'm moving with this Lorentz factor that we have here. But that's kind of cool because that simplifies a lot. That thing is going to be gamma minus 1 of t dt. Wonderful. So look what I found. Using the comoving frame, I found that d tau, it's equal, oops, that tau, let's fix it. Sometimes I'm gonna do thick taus. So that tau is thick. When you think that, tell me and I will correct it. Unfortunately, you can't tell me because you're not here in person. That is sad for me. Anyway, back on track. We found that d tau is gamma minus 1 t dt. And look at that. I related at every instant the proper frame with the lab frame, with some inertial frame, but of course the gamma factor will be different at every instant. Now this one, we're going to be applying, this is what we're going to be applying in all cases. Now, using the line element, we can write the following. We can write, of course, that the line element is, of course, this is 2 directly in the lab coordinates, in the lab frame, but we also found out that in terms of proper time, it's just minus c squared d tau squared on the previous board. So we have an equality, the line element written as proportional to the proper time intervals, well, the proper element of proper time, and also written in terms of the lab frame. So from that, we have an equality, and from this equation, we can write that d tau dt squared, it's equal to, now I have 1 minus 1 over c squared dx d tau dt squared.
Notice that this expression that I just obtained, that is boxed here, is exactly the same expression that we got on the line above. The only difference is that we have the square here. The purpose of doing this is to show that we can obtain the same relationship using 2 different set of coordinates, if you want. One using the comoving frame transformation to the inertial frame, and the other one just writing the line element in terms of lab coordinates. Okay, they are the 2 same expressions, only written in slightly different ways. But don't take my word for it. Let's actually see it.
Okay, I collected the 2 results that we got from 2 different, from the same equation doing different things, and I want to draw your attention to the fact that they are indeed the same result. Okay, because this gamma minus 1 is exactly, so if you operate on a physicist and move this dt here, again, you would get that d tau dt is gamma minus 1, and that's exactly what you get here. The square of that is gamma minus 2, all right? So this is the same equation. All right, now that said, let's see the first example. Okay, this example, the first one is going to be really easy. So if the motion is inertial, then I know that d tau is equal to gamma minus 1 of t dt, but it so happens that gamma minus 1 is a constant in this case, because in this case gamma is 1 over root of 1 minus v squared c squared, and c is a constant because the motion is inertial. So we can just integrate this being a constant, very easy. So we get that delta tau is equal to gamma minus 1 delta t. And this is, integrating that, this is exactly what you know from your previous courses in special relativity. Those are the transformations between inertial reference frames with a gamma, in which there's a gamma minus 1 between the frame that is inertial and the proper frame of the particle that's moving. Very easy. Okay, let's do an example that's more complicated. The second example, 1 plus 1 dimensional example to make it simple, is a trajectory that looks like that. This trajectory, maybe some of you can identify what kind of curve this is in spacetime, in a spacetime diagram where I have ct and x. What kind of trajectory is this? This is a hyperbola. This is actually a hyperbola starting from 0 and to some asymptote, which is the speed of light actually. In the end, it's going to be a 45-degree line. Okay? So this is a constantly accelerated trajectory. We will see that way more in depth when we actually consider non-inertial frames in special relativity, which will be the end of this block. But this is the trajectory of a constantly, this is what it looks like from the lab frame, the trajectory of a constantly accelerated observers that share an origin at time 0. They are rest with me and they start accelerating in that direction with a constant acceleration a. And this is the trajectory they will get, a hyperbola in a space-time diagram. I already computed the derivative dx dt, which gives me this. It's a very easy derivative to do. And now we can use this equation in the form 4. Okay, well, we could use either, right, otherwise, because this is kind of a step from this one if you want. But we can use 4 to compute the relationship between tau and t, and let's do it. So if we substitute, we get from this expression, taking a square root here, or directly from this expression, we get that d tau dt, it's equal to 1 minus 1 over c squared, a squared t squared, 1 plus a t over c squared. Okay, something that I get often when they look at that is like, well, this is an inverse Lorentz factor, right? So that's clearly a typo. That should be a minus because it's like the velocity is vt, is at, right? No, it's not. So don't be deceived. This is a calculation in an non-inertial frame. You would not expect to have a minus in there. Okay? We operated doing the calculation exactly at every point, and there's no mistakes in the derivative or anything. This, of course, you can say that, right, d tau, it's equal to 1 minus 1 over c squared, a squared t squared, divided by 1 plus at divided by c squared, right, dt. So I can integrate this, and if I integrate this thing, let's see that they coincide at time 0, I can obtain actually t as a function of tau. And then I get, in particular, I get tau as a function of t. Does anybody, if we were in class, we would say, do you recognize this integral? It's one of those that you should know how to do. It's a hyperbolic arc sine. So we get that this thing is c over a, the a sinh of a t divided by c, which we can invert, and we get that tau of t of tau, which is what we wanted, the time in the lab frame as a function of the proper frame, so the inversion of that relation, that would be c over a sinh of a tau divided by c. All right, and we got it. And we can take intervals now between them. All right, so this is how you relate the times, the proper time with the time in the lab frame in this example that is non-inertial. So you see how we can do it.
A little comment about the result is that you can see that in the limit of small accelerations, which is when a times tau divided by c is a small number, then the sinh is approximately equal to a tau divided by c. And then in that case, the c and the a cancel, and you get the t of tau equals tau. So basically, in the non-relativistic limit, the time is the same from both frames.
All right, let's do a third example. And a third example, again, relativistic motion gets complicated very fast. You see, this is constant acceleration and it gets complicated. Let's do some oscillations and oscillatory motion, and let's see how complicated it gets, and we'll leave it there. So let's consider oscillatory motion like this, something that in the lab frame looks oscillatory, but that's super interesting because the way it looks in in different frames may not be the same. Certainly what is constant frequency in the lab frame will not be constant frequency in any other frame, obviously. Now, of course, if the motion is described like that, we need to give it a constraint so that the trajectory is what we will call time-like later on in the next lecture. The trajectory, it never gets faster than light, okay? So you see the velocity in the lab frame is given by this expression, just the derivative. And then using 4 or 3, which is the same thing, we get the following relationship between d tau and dt. Now we can integrate this equation, and this integral that looks innocent is not so much. I'm pretty sure you haven't seen these functions too much. Most of you probably haven't. What we get as a result is this. The result of the integral is this e function of t and this argument, 1 over 1 minus c squared over L squared omega squared, divided by this quantity, where e here is an elliptic integral of the second kind that is defined like this. So it is a closed form in the sense that we know that function pretty well, but it's not easy at all. You can actually plot it if you want. This would be tau of t, okay? And of course you can invert it to get t of tau, not in closed form though. You need to evaluate to invert it. But if you were to plot it, something like that, for let's say that I take L equals 1, omega equals 0.9. If I were to plot something like this would be tau, and this would be, this is tau, this is t. As a reference, let me draw the 45 degrees line, which is if tau were equal to t, if they were not moving with respect to each other. So it does like that. It starts not moving, and it starts in the 45 degrees, but then curves a bit, then again not moving, then curves a little bit, then again not moving, curves a little bit, again not moving, as it gets faster. So, of course, don't mind my drawing skills, you can as well from alpha to plot it, but it would be something like that, and of course it's shorter time in tau. Let's say this is 60 units, so this would be 100 units, for example. So it's something like that. Of course, it accelerates a lot, gets really, really fast when it's close to the extremes of the motion, and it's co-moving with the lab when it goes to equilibrium of the oscillation, to the 0 point of the oscillation. Anyway, so I hope that these examples are clear, and with these examples you can understand much better how to transform from proper time of a particle to the lab time of a particle. Sorry, let's talk much better how to transform from the proper time of a particle to the lab frame, and in general how to do coordinate transformations and reparameterize time and transform times in terms of different time coordinates that are associated with different frames. The next thing to do is to understand better. Now we're going to start writing this in a covariant form. We're going to start doing relativity writing with index notation and covariant form. And we're going to understand better the Poincare group, hopefully. All right, I'll see you in the next lecture. Until then, take care.